The epic story of Earth's birth and evolution. A complete documentary script for BrightBoundX. Picture this, 4.6 billion years ago, in a spiral arm of our magnificent Milky Way galaxy, something extraordinary was about to unfold. Where you see our vibrant Earth today, there was nothing but a swirling disk of cosmic debris, a stellar nursery that would give birth to our entire solar system. At the heart of this cosmic dance, gravity was pulling together hydrogen and helium, compressing them until they reached a critical mass. Then, in a brilliant flash that would illuminate the darkness of space, our sun ignited for the first time. But this newborn star wasn't alone. It was surrounded by a massive rotating disk of gas, dust, and mineral particles that astronomers call a protoplanetary nebula. This wasn't just any ordinary cloud of space dust. Within this spinning disk lay the raw materials for something unprecedented, a collection of worlds that would known life in the universe. The transformation from cosmic dust to planetary bodies represents one of the most fascinating processes in astrophysics. Initially, scientists believed that planetary formation was a violent affair. Asteroids eventually harbored the crashing into each other, gradually building larger and larger bodies through catastrophic collisions. However, groundbreaking observations have revolutionized our understanding. When NASA's New Horizons spacecraft encountered the peculiar object Arrokoth in the distant Kuiper Belt, it revealed something unexpected. This dumbbell-shaped celestial body wasn't scarred by violent impacts. Instead, its smooth surface and gentle connection between two lobes told a different story entirely. Arrokoth's discovery supported an elegant new theory called gentle accretion. Rather than violent collisions, early planetary formation likely involved a more subtle process. Particles in the protoplanetary disk began clustering together through gravitational attraction, forming ever larger clumps that eventually collapsed under their own weight. These growing masses swept up additional material as they orbited the young sun, gradually assembling into the building blocks of planets. Through this process, rocky planetesimals formed in the inner solar system, while ice and gas accumulated in the outer regions. One of these inner system bodies would become our home Earth, but Earth's story nearly ended before it truly began. Approximately 4.5 billion years ago, when our planet was still in its infancy, a Mars-sized object that scientists called Theo was hurtling through space on a collision course with Earth. The impact was beyond imagination, equivalent to billions of nuclear weapons detonating simultaneously. The collision occurred at an oblique angle, which proved crucial for what happened next. Rather than completely destroying Earth, this catastrophic event liquefied our planet's surface, creating a global ocean of molten rock that glowed like a star. But from this apparent destruction came something beautiful. The tremendous force of impact hurled massive amounts of molten material into space, where it remained captured by Earth's gravity. Over time, this debris began to coalesce through the same accretion process that had formed the planets themselves. What emerged was our moon not as a separate captured body, but as Earth's own child, born from the violence of cosmic collision. In those early days, our lunar companion loomed enormous in the sky, appearing nearly 16 times larger than it does today and generating tides that would dwarf anything we experience now. This giant impact theory explains many of the moon's peculiar characteristics, why it's depleted of volatile elements like water and nitrogen, they boiled away during the impact, why its composition so closely matches Earth's mantle, and why it always shows the same face to our planet. The aftermath of the moon-forming impact left Earth in a state that can only be described as hellish. This period, appropriately named the Hadean Aeon after Hades, the Greek god of the underworld, lasted from Earth's formation until about 4 billion years ago. Imagine a world where the surface temperature exceeded 200 degrees Celsius, hot enough to keep rock in a molten state. The atmosphere was a toxic brew of carbon dioxide, carbon monoxide, sulfur compounds, and other volcanic gases, with pressures many times greater than today. The landscape was dominated by countless active volcanoes, spewing lava and ash into the poisonous sky. Yet even in this seemingly impossible environment, something remarkable was happening. As Earth began to cool, water vapor in the atmosphere started to condense. The first clouds formed, marking the beginning of a process that would transform our planet forever. When the surface temperature finally dropped below water's boiling point, the first rain began to fall. But this wasn't a brief shower, it was a deluge that lasted for thousands of years. Steam rose from the superheated ground as endless torrents of water carved the first rivers and began filling the lowest areas of the cooling crust. Gradually, permanent bodies of water formed, first small lakes and ponds, then larger seas, and finally vast oceans that covered the entire planet. By the end of the Hadean Eon, Earth had transformed from a molten hellscape into a water world, completely covered by a global ocean with no dry land in sight. The presence of vast oceans on early Earth presents one of geology's most intriguing puzzles. If our planet formed in the hot inner solar system, where did all this water come from? For decades, scientists proposed that comets, those dirty snowballs from the outer solar system, delivered Earth's water through bombardment. This seemed logical. Comets contain large amounts of ice, and we know Earth was heavily bombarded by celestial objects in its early history. However, detailed analysis revealed a crucial flaw in this theory. Water molecules aren't all identical. Some contain deuterium, a heavy isotope of hydrogen. The ratio of deuterium to regular hydrogen acts like a fingerprint, unique to different regions of the solar system. When scientists measured this deuterium ratio in comets from the distant Oort cloud, they found it was completely different from Earth's water. Even comets from the closer Jupiter family showed inconsistent results. Some matched, others didn't. The asteroid hypothesis initially seemed more promising. Asteroids from the belt between Mars and Jupiter showed deuterium ratios much closer to Earth's oceans. But timing problems emerged. The proposed late veneer of asteroid bombardment occurred too late to account for oceans that we now know existed much earlier. The most likely explanation represents a fundamental shift in our understanding. Earth's water was here from the very beginning. Deep within our planet's interior, hydrogen and oxygen were trapped in the crystal structures of minerals during Earth's formation. As these minerals melted in the planet's hot interior, they released water vapor that reached the surface through volcanic outgassing. In essence, Earth didn't need to import its water from space. It was carrying the ingredients for oceans within itself all along. As Earth cooled and stabilized, the first solid ground began to emerge from the global ocean. Volcanic activity didn't cease. Instead, it became more focused and less chaotic. Underwater volcanic vents began building submarine mountains, which eventually grew tall enough to break the ocean's surface. These first islands were nothing like the lush tropical paradises we might imagine. They were barren volcanic cones, constantly reshaped by eruptions and erosions. But they represented something revolutionary, the first dry land in Earth's history. Over millions of years, these isolated volcanic islands gradually expanded and merged through continued eruptions and the accretion of volcanic material. The first protocontinents began to take shape, small land masses that would serve as the nuclei for the much larger continents we know today. This process marked the transition from the Hadean to the Archean Eon, a period that would witness Earth's next great transformation, the emergence of life itself. Around 3.824 billion years ago, in the seemingly hostile environment of early Earth, something miraculous occurred. The first living organisms appeared. These weren't complex creatures. They were microscopic prokaryotes, single-celled beings without nuclei or specialized internal structures. Yet these simple organisms possessed all the fundamental characteristics of life. They could metabolize nutrients, maintain their internal structure, respond to their environment, and most importantly, reproduce themselves. The key to their existence was the development of ribonucleic acid RNA, a remarkable molecule capable of both storing genetic information and catalyzing its own replication. RNA served as both the blueprint and the construction machinery for these early life forms, solving the classic chicken and egg problem of which came first, genetic information or the means to copy it. These pioneering microorganisms faced challenges that would kill any modern life form instantly. They lived in an atmosphere devoid of oxygen, under constant bombardment by ultraviolet radiation from the sun. There was no protective ozone layer, and in environments filled with toxic chemicals. Yet they not only survived but thrived, establishing themselves in every available ecological niche, from the ocean floors to underground rock formations. Some of these early organisms even learned to harvest energy from sunlight, developing the process of photosynthesis that would eventually transform our entire planet. Between 4.1 and 3.8 billion years ago, Earth may have faced its greatest test, a period of intense asteroidal and cometary bombardment known as the Late Heavy Bombardment. During this time, massive space rocks, some over 500 kilometers in diameter, regularly struck our planet with devastating force. Each major impact would have boiled away oceans over vast areas, created global clouds of superheated rock vapor, and triggered worldwide tsunamis. The returning debris would have created fiery meteor showers that made the surface uninhabitable for extended periods. How did life survive such catastrophic conditions? The answer lies in the remarkable resilience and adaptability of these early microorganisms. Many lived deep underground, in rock formations that provided natural shelters from the chaos above. Others survived in the deep ocean, far from the direct effects of surface impacts. Perhaps most importantly, the intervals between major impacts were long enough, tens of thousands to millions of years, for life to recover and re-establish itself across the planet. Even today, the vast majority of Earth's microbial life exists in following the surface environment. A survival strategy that allowed life to persist through this violent period. Recent research suggests that the late heavy bombardment may not have been as severe as once thought, or may not have occurred at all. But whether life faced this trial by fire or not, the fact remains that it successfully established itself on Earth and never again faced extinction. Around 3.5 billion years ago, a group of microorganisms called cyanobacteria began performing a process that would fundamentally alter Earth's destiny: oxygenic photosynthesis. Unlike earlier forms of photosynthesis that used hydrogen sulfide or other chemicals, cyanobacteria split water molecules to obtain hydrogen, releasing oxygen as a waste product. Initially, this oxygen didn't accumulate in the atmosphere. Instead, it reacted with dissolved iron in the oceans, creating rust-colored iron oxides that settled to the ocean floor. These deposits, called banded iron formations, created alternating layers of iron-rich and iron-poor sediments that tell the story of ancient photosynthetic activity. For nearly a billion years, cyanobacteria continued this process, gradually consuming all the dissolved iron in Earth's oceans. Then, around 2.4 billion years ago, something dramatic happened. The iron ran out, and oxygen began accumulating in the atmosphere and oceans for the first time. This great oxygenation event transformed Earth in ways that are difficult to comprehend. The accumulation of oxygen in the atmosphere created the ozone layer, providing protection from harmful ultraviolet radiation for the first time in Earth's history. The oceans changed from rusty green to brilliant blue. Even the sky changed color as atmospheric chemistry was revolutionized. But this transformation came at a terrible cost. To most existing life forms, oxygen was a deadly poison. The Great Oxygenation event likely caused Earth's first mass extinction, wiping out countless species of anaerobic bacteria and archaea. However, for the organisms that survived and adapted to use oxygen, this crisis became an unprecedented opportunity. Oxygen-based metabolism is far more efficient than anaerobic processes, providing the energy necessary for more complex life forms to evolve. The increase in atmospheric oxygen had an unexpected consequence. It triggered one of the most extreme climate events in Earth's history. Oxygen reacted with and removed greenhouse gases like methane from the atmosphere, while the formation of the first large supercontinent, Kennerland, accelerated the weathering of rocks, which consumed even more carbon dioxide. With dramatically reduced greenhouse gas concentrations, Earth's climate system lost its ability to retain heat. Global temperatures plummeted, and ice sheets began forming at the poles. But this wasn't an ordinary ice age, it was a runaway cooling event that didn't stop until ice covered the entire planet from the equators to the poles. This snowball Earth state, known as the Huronian glaciation, lasted from 2.42 to 2.1 billion years ago. For 300 million years, our planet was a frozen wasteland, with ice covering even tropical oceans. Surface temperatures may have dropped to -40 degrees Celsius or lower, several kilometers thick. How did life survive this ultimate frozen catastrophe? The answer lies in the remarkable tenacity of microbial life. Even in a completely frozen world, pockets of liquid water persisted near volcanic hot springs and geothermal vents. Some microorganisms survived in subglacial lakes, similar to those found beneath Antarctica today. Others found refuge in microscopic melt pockets within the ice itself. Earth escaped from its frozen state through the same volcanic activity that had helped trigger it. Throughout the glaciation, volcanoes continued pumping carbon dioxide and other greenhouse gases into the atmosphere. Eventually, these gases reached concentrations high enough to begin melting the global ice sheet, starting a rapid warming that restored our planet to a more habitable state. Around 1.8 billion years ago, life took its next great evolutionary leap with the emergence of eukaryotic cells. Unlike the simple prokaryotes that had dominated Earth for over 2 billion years, These new organisms possessed internal structures called organelles, including a nucleus that housed their genetic material. The most important of these organelles were mitochondria, specialized structures that could efficiently process oxygen to produce energy. Scientists believe mitochondria were originally independent bacteria that were engulfed by larger cells in a process called endosymbiosis. Rather than being digested, these bacterial prisoners became permanent residents, providing their hosts with the ability to harness oxygen's powerful energy-producing potential. This partnership was revolutionary. Eukaryotic cells were not only larger than prokaryotes, up to 10 times bigger, but they also had access to far more energy. This energy surplus would eventually enable the evolution of complex multicellular organisms. The earliest eukaryotic fossils, collectively known as acritarchs, appear in rocks around 1.8 billion years old. These microscopic organisms displayed a variety of shapes, some smooth and spherical, others covered with intricate spines and projections. They represented Earth's first experiments with complex cellular architecture. One particularly intriguing organism from this period was Grippania spiralis, a long, ribbon-like creature that could reach several centimeters in length, making it visible to the naked eye and possibly the first large organism in Earth's history. From 1.8 billion to 800 million years ago, Earth entered a period that paleontologists have dubbed the Boring Billion. This wasn't because nothing was happening, but because evolutionary progress seemed to stall. No major new life forms appeared, and atmospheric and oceanic chemistry remained relatively stable. The reason for this apparent stagnation lay in Earth's atmospheric chemistry. While oxygen was present, its levels remained relatively low, high enough to prevent the return of anaerobic conditions, but too low to support the energy demands of complex multicellular life. This occurred because oxygen-producing cyanobacteria were competing with sulfur-metabolizing bacteria and methane-producing archaea. The oceans were stratified, with a thin, oxygenated surface layer overlying vast volumes of oxygen-free deep water populated by anaerobic microorganisms. But appearances can be deceiving. During this boring period, several crucial developments were taking place. Sexual reproduction evolved, allowing organisms to exchange genetic material and accelerate evolutionary innovation. The first red algae appeared, followed by green algae, the ancestors of all land plants. By the end of the Boring Billion, oxygen-producing organisms had finally gained the upper hand over their anaerobic competitors. Atmospheric oxygen levels began to rise significantly, setting the stage for the next great revolution in Earth's biological history. Around 750 million years ago, Earth once again succumbed to global glaciation. Unlike the earlier Huronian event, this Neo-Proterozoic glaciation, known as the Cryogenian period, involved at least two separate snowball episodes. The causes were similar to the earlier glaciation. The breakup of the supercontinent Rodinia increased weathering rates, removing carbon dioxide from the atmosphere. Rising oxygen levels further reduced greenhouse gas concentrations. The result was another frozen planet, with ice covering even equatorial oceans. But life was no longer the simple collection of microorganisms that had survived the earlier snowball. By this time, eukaryotic cells had diversified considerably, and some had even begun experimenting with multicellular organization. The cryogenian glaciations may have actually accelerated evolution by creating intense selective pressures. When the ice finally melted around 635 million years ago, the stage was set for the most dramatic biological revolution in Earth's history. In the aftermath of the final Snowball Earth event, something unprecedented occurred in Earth's oceans: the emergence of large, complex, multicellular organisms. The Ediacaran period, named after the Ediacara Hills in Australia where many fossils were first discovered, witnessed the appearance of life forms unlike anything that had come before or has existed since. These creatures, collectively known as the Ediacaran biota, were truly alien by modern standards. Some, like the rangomorphs, exhibited fractal body plans that repeated similar patterns at multiple scales, a design unknown in any living organism. These strange beings lived in the deep ocean, far below the reach of sunlight, and likely fed by absorbing dissolved organic molecules directly through their skin. Fractophysis could reach 40 centimeters in length and connected to its offspring through thread-like filaments. Charnia resembled giant ferns swaying in the deep-sea currents, reaching up to 60 centimeters in height. The massive Primocandelabrum towered 2 meters above the seafloor like an alien tree. Later in the Ediacaran, a different type of organism appeared, the Proarticulata. These pancake-like creatures, including the famous Dickinsonia and Georgia, lay on top of microbial mats and apparently fed by absorbing nutrients through their skin. They had bilateral symmetry and could move, leaving behind fossil tracks that proved their mobility, but they lacked mouths, guts, or any recognizable sensory organs. Recent chemical analysis of Dickinsonia fossils has revealed the presence of cholesterol, strongly suggesting these creatures were indeed early animals. If so, they represent the first large animals in Earth's history, even though they were unlike any animals alive today. Most remarkably, a tiny worm-like creature called Icaria wariusha has been discovered in rocks from this period. Only a few millimeters long, this unremarkable-looking organism may be the direct ancestor of all modern animals, including ourselves. As the Ediacaran period drew to a close around 540 million years ago, these strange experimental life forms were gradually replaced by more familiar creatures. The Cambrian explosion was about to begin, marking the start of the Phanerozoic Eon, the period of visible life that continues today. The stage was now set for life to colonize every possible environment on Earth. Over the following 540 million years, organisms would emerge from the oceans to colonize the land, take to the skies, and eventually develop intelligence sufficient to understand their own origins. The long journey from cosmic dust to conscious beings represents one of the most remarkable stories in the universe. Every atom in your body was forged in the nuclear furnaces of ancient stars. The water you drink fell as rain during Earth's first storms 4 billion years ago. The oxygen you breathe was produced by cyanobacteria that lived and died countless generations before the first animals evolved. We are not separate from this cosmic story. We are its most recent chapter, temporary custodians of the consciousness that allows the universe to know itself. From the violent birth of our solar system to the emergence of complex life, Earth's 4.6 billion year journey represents an epic tale of transformation, survival, and innovation. Every major crisis, the moon-forming impact, snowball Earth events, mass extinctions, and atmospheric revolutions ultimately became an opportunity for life to evolve in new directions. Today, as we face our own planetary challenges, we can draw inspiration from life's remarkable resilience and adaptability. The same creative forces that transformed a molten hellscape into a vibrant, life-sustaining world continue to operate today, both in the natural world and in the remarkable capabilities of human intelligence and cooperation. We are the universe's way of understanding itself, the culmination of billions of years of cosmic evolution. Our story is far from over. In many ways, it has only just begun. If this incredible journey through Earth's deep history has amazed you as much as it has amazed us, show your support for BrightBoundX by hitting that like button. This epic story deserves to be shared. Help us spread scientific wonder by sharing this video with friends, family, and anyone curious about our cosmic origins. And don't forget to subscribe to BrightBoundX and ring that notification bell, so you never miss our latest explorations into the mysteries of science and the universe. Together, we'll continue uncovering the remarkable stories written in stone, stars, and the very atoms of our being. Thank you for joining us on this incredible journey through deep time.